So earlier we saw a method of preparing simple anhydrides just by dehydrating simple carboxylic acids. Well, a much more general way of making anhydrides is by a nucleophilic substitution reaction. If our nucleophile is a carboxylate ion, right here, CH3C double bond O minus, that's sodium acetate. What it can do is attack the carbonyl of an acid chloride, brings those electrons up. Chlorine is the leaving group in the second step. That substitutes the chlorine for this acetate group. So that gives us acetic benzoic anhydride because we started with benzoyl chloride, a derivative of benzoic acid. So we can use this method to produce really any anhydride we want. It can be symmetrical or unsymmetrical, right? If we use a different R group in our acid chloride from our carboxylate, we can very easily make a unsymmetrical anhydride. So if we wanted to sort of do this from scratch, from carboxylic acids, of course, we would take acetic acid, CH3C double bond OH, and deprotonate it with sodium hydroxide. They actually drew the sodium here, so let's say NaOH. That'll give us sodium acetate. We could always also, for the acid chloride here, for benzoyl chloride, we could do benzoic acid and thionyl chloride, SOCl2. So by taking two carboxylic acids, deprotonating one with base, making an acid chloride out of the other, and then reacting them together, we can get an anhydride. Pretty slick method. Since anhydrides were second from the top on our list of most reactive carboxylic acid derivatives, we can make anhydrides really favorably into any of the other derivatives except acid halides. So otherwise, with all these other ones, reactivity of anhydrides is very similar to the acid halides we were just talking about. So if we imagine the leaving group here as containing the oxygen as well as a C double bond O and the R beyond it, if we call that our leaving group of the anhydride, then really any other nucleophile can attack the other carbonyl, replacing it. So if we do water with an anhydride, we get a carboxylic acid. If we do an alcohol, we get an ester. An amine, we get an amide. By reduction, we can get an aldehyde or all the way to a primary alcohol. First, let's talk about anhydrides into esters. It's a very common usage in order to use an anhydride to add a simple acyl group onto an alcohol. Right, that makes an ester. So if we have salicylic acid, for instance, this is how aspirin is made commercially. Here's salicylic acid. It has an OH group right there. That's our nucleophile. We react it with acetic anhydride. The OC double bond OCH3 is our leaving group. We'll essentially just replace the leaving group with the rest of this alcohol here to make an ester. We've added an acetyl group. Right? That's C double bond O CH3. We can add an acetyl group onto an alcohol with acetic anhydride. Okay? So pay close attention to that reaction. Notice the carboxylic acid over here is untouched. Carboxylic acids, when they're neutral, like this, are not very strong nucleophiles. The oxygen's electrons are tied up in its secondary resonance structures, whereas this alcohol here has a lone pair of oxygens that are ready to attack the anhydride. So if ever we need to make OH into O C double bond O CH3, that's also sort of a way of protecting an alcohol, right? We can go O, this is also referred to here as OAC, that's C double bond OCH3, because with some aqueous acid, we can cleave this ester and get back to the alcohol. If I want an acetamide, we can do that just very similar to what we did up above. Right? Here is parahydroxyaniline, lone pair on the nitrogen. We also have an OH group. Remember what we've talked about. Nitrogen is a stronger nucleophile than oxygen is. So it'll attack the carbonyl of acetic anhydride. The rest of it is the leaving group. And after a proton transfer, we'll have NH C double bond O CH3. So let's just, for kicks here, let's carefully draw that mechanism. So here's the hydroxyaniline, NH2. That nitrogen has added to the carbon right here. So we have an alkoxide, O-. It already had a CH3 on it. The leaving group is OC double bond OCH3. So O- comes back down, kicks out the leaving group. Be careful here. After the nitrogen attacked, it was an NH2 plus. So let's draw the immediate product here. HO, benzene, NH2 plus, C double bond O, CH3. It is the extra base here that deprotonates that N to give us the neutral amide, just like that. Okay. Plus, it's always a good idea to draw the leaving group that left here. Okay. We have an acetate ion that's floating around because that's going to have to be purified out.